And now we're going to set the boundary conditions and the material property, and they are connected by Reynolds number. And we define Reynolds number as rho v d upon mu, where mu is the dynamic viscosity of fluid and the rho is the density, and the v is the velocity of incoming fluid in this double contraction U-bend pipe, and v is the velocity and d the diameter. And as I explained earlier in the previous videos, previous workshops, that we set Reynolds number in Fluent by this method. Now, for example, we have Reynolds number equal to 10,000. And so 10,000 is a value because the Reynolds number, when becomes 4,000 for internal flow, the flow becomes turbulent. And when the Reynolds number is less than 2300, the flow is laminar. And in between 2300 and 4,000, the flow is transitional. And we don't want to be just on the edge of that Reynolds number range. So I just put the Reynolds numbers at some higher value than the 4,000. So my safe bet is that 10,000. And I'm taking density as a 1,000 now. It's your choice. You can take any value, but as far as the Reynolds number is same, the results will be same. And here I've taken, because it's a liberty of CFD, that you can put any value for the material properties, and which is not the option you have in the wind tunnel testing or in the lab. So therefore I have taken the density as a 1000, velocity as a 1, and the velocity value should be less than, in such a way, so the Mach number should be less than 0.3 or maybe within the below 0.3, so that flow does not become compressible at any point. Because for compressible flow there are the many other things we should be considering, like the density will be variable and there are many things there. So therefore I'm just at the very low value of velocity, and therefore there will be low value of the Mach number here. And diameter of pipe of this larger pipe is 1 meter. And so why not this small diameter? Because the majority of the pipe length is with this diameter of 1 meter, and therefore I've taken this value. Now remaining thing is the viscosity, or dynamic viscosity. So I can solve for the viscosity from Reynolds number formula, and so I get the value of viscosity as a 0.1. So now we set these values in Fluent, and so first of all I would set the value. So you can just keep the name as a air, or you can change the name to the fluid, and then just click on change create, and this will create a new fluid here, new material properties here. And here I'm going to put the value of density as a 1000, as I've shown you in the slide, and the value of viscosity I'm going to use is a 0.1, and this is because I need to make the Reynolds number equal to 10,000. And then from the boundary condition, only setting we need to do is the inlet condition, and for that we have the velocity is equal to 1 meter per second, and click on OK. And also we need to change the modulus from for viscous to the SST K omega, or you can go for the K epsilon with the lysable and in asphalt treatment. So let's say we go with this model, that is the K epsilon realizable and the asphalt treatment, and click on OK. And when we choose the realizable K epsilon model, this is a very good model here. And the asphalt treatment means that this is a wall function, this is a hybrid wall function, and when the y plus value is less than 5, it will go for the viscous sublayer, and when it's between the value of 5 and 30, it will apply the balance between the wall functions and the viscous sublayer, and so that we can solve for the buffer layer. And when y plus 30, so it will implement a simple standard wall function. So we have set the boundary conditions, we have set everything else we needed to set, and by default the method is a coupled, which we will keep here. And so we initialize solution from, let's say, from inlet, or you can also use hybrid, which is a much better method for the most of the CFD problems. And then we run the calculation. Before that, I'm going to, from the monitors, and for residuals I'm going to change the value of residuals to some lower value, so that the solution does not stop by its own choice. So without converging solution, I mean to say that if the conversion criteria 0.001 is satisfied, the solution will be stopped. But I want to run this case for some required number of iterations, which I think will give me the converged solution. So this is the only thing I wanted to say here. And then run solution for let's say for the 500 iterations, and click on calculate. And so far the number of iterations we have for 55, and it's continuing, and we can stop here. And as you can see that the result plots, they are now almost straight, they are almost flattened. So we need some other parameter or some variable on basis of that we can ascertain the convergence of our problem. And so first of all, let me display this mesh here. And my idea says that we should put some point here, let's say in this value, in this area. And if that value converges to, or it's straight, or after some iterations its value is constant, or with the flow is transient, then its value should be changing with some constant pace. And so we have, if I calculate the value of that location, I can see the radius is equal to 0.75, length of this pipe is 20 meters, and from here, so I can be at the location of the center when z is equal to 20.75. So therefore I'm going to create a 1 point, and that point I can create from results and create, and I'm going to create a 1 point. And the first location I would put is the 20.75. It's a x, and in the y, it's right now it's at this location the value of y is equal to 0, because the diameter is 1. So at 0.5 this value will be equal to the, at 0 it will be origin, and below this value the equal to the radius will be minus 0.5 in the y direction, and up to here it will be the 0.5 plus 0.5. So therefore up to from this point to this location of radius is equal to 0.75. So 0.75 plus 10 will be equal to 10.75. And in the z direction, this should be done in the z direction, this value, x value, 20.75 put here, and the x location, it should be equal to 0, because we want to put this value just on the center value or center plane. And click on create, and now just display this value where this point is located. In fact, I just want to confirm this value, and you can see this point is in the center plane, and in the second pipe, in the vertical pipe, and just over here. And for that I'm going to create a report definitions. Right click here and click on new, and I'm going to put the surface report, and I'm going to put the vertex average value, because the single point vertex average, and I want to monitor the value of velocity or maybe value of pressure. So let's say I want to monitor value of velocity here on point number 7, and I want to write down the report file, and report plot means the plot will be displayed on the screen here, and that is to be done after every iteration, right? And I want to print to the console, that is the print in this text user interface, and we have the vertex average, everything is okay, velocity magnitude 0.7, and click on OK. And one more thing, you can see that we have this thing here, that you can also make a output parameter. That is, I told you in the very beginning of this workshop that you can make some parameter the output and some parameter the input. So when we apply the parametric solution, in that case we want to see the change of geometry or change of mesh, and then the results change with that variable, and that variable, output variable, can be displayed from here. Now click on close, and again apply the solution and calculate. And now you can see that this vertex average is being plotted in a plot on the screen. And if this value does not go in a straight line, that is a flattened curve here, a flattened graph here, then we can see that solution has the transient nature or unsteady nature. That is when there is separation bubble, which is obviously with that is double contraction, and the U bend and the not a U bend but 90 degrees bend. So it's very obvious that the flow will become an unsteady flow or transient flow. In that case, we don't get the convergence in a straight line. Rather, we get the convergence which is called as the periodic convergence, means that the value will vary between some range, and then after some interval it will repeat itself to some value. In that case, we have to run this case as the transient case. But right now I'm not going to do that thing, but I just want to show you that what can happen, and in that case how you can understand the things. And so your call should be that you should be running the transient case and runs case for the some several time steps, and then every data for those time steps you will get the average value or time mean value of that variable on that location. And I ran this case for around 2635 iterations, and after that I can observe some pattern here, and I just put it on the PowerPoint slide. And if you take a look on here, you can see that after this is a pattern here we have here, and this peak here, then this peak, this is still somehow little peak here, but almost similar. And then we have the something like this, and also something like this over here. So I can say that from here to here we have the one interval, and then the second interval is also replicating the some first one. And therefore what is the strategy in this case is that we have to run this case transient, but I will not be doing that thing. Why? Because my purpose is not here to give you idea about the transient data and how to solve it and how to post-process it. That is coming in this next tutorial in the flow around a circular cylinder. But here I'm just wanted to tell you that how you can observe the things that the steady solution is not possible, and we have to go for transient solution. And then the second cycle will be like that. And we have to observe this solution for at least 5 similar cycles, like this one in the red color, then second one in the red color, third, fourth, fifth. You have to store data in your some file. Open that file in the Excel, and for number of iterations and number of time steps, just add these values and then divide them by the number of the iterations, let's say 1000 iterations, or maybe it's a 200 time steps, and divide by them these number of time steps or number of iterations, and you will get some data which is the average data there, and that is the data we need. So for example, might be you come up with some value and you say that this is my average value of velocity at this point, and so I can say this is around 0.65 or 0.655. So this is a value of average value of from this point at that location, and this is how we do the transient simulations. Okay, now we move to our simulation, and then we will make some post-processing in the Fluent, some basic level of post-processing, and then some post-processing in the CFD post. And if you want to go for the more details and the extensive type of the post-processing, then you should refer to that 9 degrees bend tutorial with the small lead. That will give you the very good idea about how to post-process results in the very good details.